Good evening to everyone. I'm Chalaya Thomas Rushwin. I'm from IIC Bangalore. My PA is Dr. Tanmay Das sir. Today I'm going to present my topic on machine learning reconstruction of magnetic and superconducting domes in quantum materials. Basically, using machine learning, I'm going to find what are the factors that is, what are the features that is going to be useful in the unconventional superconductors. So the introduction. So what motivates me and others? So first of all, we know what is meant by superconductivity. We know that when the materials has a zero resistance below a certain critical temperature is called superconductivity. But we are having a class of materials called unconventional superconductivity, which deviates from the normal superconductive conductors because it doesn't follow the BCS theory. And instead of that, it people are for many years trying to find the universal thing like BCS thing and everything, but still the research is going on. In 2016, Das and Panagopoulos proposed that there are many unconventional superconductive have two domes. Like here, it is showing two domes, and these two domes are can be observed while the QCP, that is a quantum critical point, where at 0 Kelvin, with the tuning parameters, we can find the two domes like doping or pressure or any other thing other than the temperature fluctuation. So there is also a crossover between the visibly, it was visible in the resistivity that you can see here. So what I am going to do now, I am going to verify whether those claims are correct or not in terms with the machine learning. So as we know, the machine learning is one of a blooming uh, field, and here it uses the statistical model to predict and classify and everything whether the materials are giving some things. And here I am using SAP analysis, which is a shapely additive explanation. Here we can know which features contributes more to the prediction and which features are not contributing more to the predictions. So here what I am basically going to do is I am going to classify whether the materials are giving a correct features or not. So for that I have used totally 18 models, which is based on tree based models and other models like neural network. This is a basic neural network. Here I have also used, with the combination of this, I have created the ensemble, and I have used to find whether every materials are giving a similar kind of results or it deviates from models to model, because each model has its own properties or own ways of classifying everything. So here I have used group k-fold, and this is one of a cross validation that many people, if you see in the talk, they have mentioned like CV. Here I have used group k-fold because in this normally whenever they are doing, they will do stratified, which means they are having only a certain families there. It will like if there's only 1,000 in a box, it will separate like that in the data set. But here I am having as the data as families, which I will explain in the next slide. Here for SAP, actually I am using SAP analysis. So here for the benefit of very easy integration, I am using tree SAP for the tree based models and kernel SAP for neural network and KNN. From that I will get the what is the most good features are used here. So this is my data set, which consists of 4 different families. Here you can see that is cuprate, iron picnite, heavy fermions, and organic KET. Here the tuning parameter, which was similarly observed by Das and their group. Here you can see these are the tuning parameters. Everything starts from this, because here we can see this is the resistivity curve formula. Here this is the residual resistivity, which is an extrapolation of the resistivity curve when after the superconductivity is achieved. And here this n, which is very useful because we can see that normal superconductor, most of the things follows n is when n leads to 2, which is a Fermi liquid. But when near to after the second first dome, that we can see it also shows the non Fermi liquid kind of thing near the QCP. So here totally okay. So what I am going to do in the methodology section means I have done in uh, three separate ways, where I have used a raw grid, where I just um, modify every, because each experimentalist has a different data and they have a different tuning parameters and other things. So I like different temperature ranges. So I merged it with a clear. We have labeled it and we created one raw grid for that consists of 157 features, and we created another one physical scalar that is very like T star and other things using that has around 35. With along with that we are also used compositional features. So what happening means, first with the registered data we will train in with the raw grid, then training, then followed by SAP and the result, then the second workflow which is only with physical scalars, the same thing. And the other it has a three different workflows. So here I have mentioned loco and lofo, which is leave out compound out. So whenever we are leaving out a certain compound and we have to find whether the model can learn by itself. So I left out a model, like left out a compound and find whether the predicted features are universal or not. And another one is lofo, that is a leaving out of family. So does these four families have anything in common, so that we can find using this. So this is the classification performance. I did this for the only the physical scalar. Here you can see the ROC value. This is the curve, that the area of the ROC curve. That means if you are in the present in the Umesh Wagmare sir's lecture, he used that classification model, that true positive, true negative, false positive, false negative. From that we will get this we will create this area under ROC curve. From that we have calculated using this different 18 models. As I have no space, so I just putting only one. Here you can see, as I said, that 157 features, and the best model which is performing is 0.8. So what is the best value means, when ROC is approximately equal to 1, then then the model is good and the data sets are good. So according to this we can see the raw data is giving a 0.8, whereas the physical scalar is improving it by including the compositional feature. It's also increasing and it's making approximately equal to 1 sometimes. So these are the things. So the next one is the feature importance. So here you can see the first features. So this is the first thing, and in the SAP analysis here you can see the tuning related to the QCP. That means the distance between the QCP, that is the prominent feature. That was the thing that was what in the 2016 um, in that work they have mentioned. So with this was done, and here you can see the some compositional feature also giving some importance that can be seen here. Next, the cross, as I said, that loco and lofo. Here I used that I am mentioning that lofo. Here we can see that when we are leaving out the cuprates and we are finding it, we are getting that 1 and 0.7 and 0.8. And mostly here you can see from this model in the ORAC for different materials. Here you can see the most things like cuprate was predicted somewhat decently, and organic also, and pignite was somewhat good, but heavy fermions are very less. That is due to the low data set. This is belongs to the data set row, and here this is low the leaving out a compound. By leaving out this and finding, we can find how much it was predicted. So this model is overfitting. The MLP is overfitting, because sometimes when we are getting one, that might be a overfitting one. And the conclusion and the future direction, right now I am working on this, and from here I have concluded that the tuning related to the QCP is the dominant feature, and the loco and confirm that the physics can be transferred. Like for everything I am getting this one as a number one dominant feature, and in future I am trying to extend it and other things too. And I need to acknowledge my uh, guides group and my PhD group, that Das group of quantum matter theory, and IIC Bangalore for the computational facilities and everything, and the QMET for the opportunity to present. Thank you.
Thank you. It's open for questions. Any question? If there are no further question, then we move to the next job by Kaushik Dash.
Start. So, good evening, everyone. So, my name is Pavan Kumar Patra. I'm a PhD student at IIT Bombay. So, I'm about to graduate soon. This work is done basically with my supervisor, Professor Hitesh Kumar Pal. So, my title of talk is Moray-induced topology in Moray ladders. So basically, I like to give a disclaimer to the audience. So this is not the current science theme which is this session going on, but because of the tight schedule, I am given this theme. So let's go to the what is a Moray ladder basically. So Moray ladder is basically a two-leg ladder where T is the interleg hopping in each chain, and there is a spatial modulated interleg hopping given in gamma j form. So here gamma node is the constant interleg hopping. This basically contains two main ingredients. One is more periodicity, one with flux. So this exponential part gives the flux. This capital gamma just to turn on or off the flux. This has no physical meaning. So gamma equal to 0 means no flux, gamma equal to 1 means flux. And this small g is the prefactor of the Moray periodicity. Small j is the site index. Capital J sets the Moray periodicity of the ladder. Right, and the gamma node is the constant interleg hopping. So, sigma is the spin index, lambda is the leg index. So far now, by Moray, people have understood Moray periodicity. So because in this model, I can decouple Moray periodicity as well as the Moray flux individually. So henceforth, I'm going to discuss this Moray ladder in these two aspects. One with no flux, that means capital gamma equal to 0. One with flux. So let's see the low energy Venn diagram of this model and how it resembles with the name given, basically twisted Euler graphing. So when you start with basically two degenerate adwinding chain, basically the energy will be 2 t cos k. Then when you impose constant interleg hopping, the energy will shift along, the band will shift along energy direction. And then when you give a prefactor of Moray periodicity, because of Bragg scattering, the band gap will open up. Now with flux, first there will be a momentum separation will happen, and because of the constant interleg hopping at the band touching point, a band gap will open, and similarly as the no flux case, because of Bragg scattering, band gap will open up. Now there is a qualitative difference between these two cases. One can see in the no flux case, while all the bands are bandwidth of same order of T by J, T is the hopping parameter, capital J is the periodicity. Here one can see the lowest band is qualitatively remain flat than the upper dispersive bands. And so how it compared with TBG? Let's see. So in TBG band diagram, what happens? When there is a rotation in real space, there is also a rotation in momentum space. This del k is the vector is the connecting two Dirac points. K and k theta are the Dirac points of unrotated and rotated layer respectively. This del k basically sets the length of Moray zone, Moray periodicity. So similarly, there will be a momentum separation in TBG where by vector del k, and because of the interleg hopping, and when you go to the low energy, especially at magic angle, because of the band repulsion, this actually at half filling, it will become quasi flat. Now one can see the emergence of emergence of the quasi flatness is similar with flux case with TBG. So henceforth, I am going to compare, because of the analogy only, the half filling of TBG with the actually the lowest band of the in the Moray ladder itself. Now what is this advantage of Moray ladder with actual TBG? Sorry. So in actual TBG, what happens? There are basically lots of degrees of freedom. Dirac physics are there, sublattice degree of freedom is there, and because it has an inherent topology, the one-year function are not well localized, so it doesn't help to write a effective real space lattice theory. So what does our model offers basically? So our model offers in a simplest way to capture the Moray essential ingredient. One can see each layer of how this Moray ladder basically formed. Each layer of graphene is replaced by 1D chain, and so forget about Dirac physics, everything very degree of freedom. But the main ingredient Moray potential as well as the complex phase is given by this gamma R, which I have discussed explicitly in the last slides. So this gives extra advantage as in form. Here in 1D model, it is more controllable. One can do DMRG to find interacting physics. And one special thing is here one can decouple the Moray periodicity and the flux they can decouple it in this Moray ladder itself. However, in the TBG, because it comes from the exponential e to the right del k term, they both come from the same term, so it is impossible to decouple it in actual TBG problem. So that's why this model is of interest in our model. In my case, so I'm henceforth I'm going to talk about only this model, not about TBG. So this model has been studied on also recently, and two main non-trivial results were found. there is a finite two mode transition which is unlikely to 1D Hubbard model. And ferromagnetism at a half filling of the lowest band. This is at actually lowest band. This has been done in these two work, but for this talk I am going to focus on the ongoing work which is basically topological aspects of the Morel ladder. Now, so in TPG, each layer of graphene at each value point there is a vary phase. So it comes from the each single layer of graphene. To see in our model, the topology can come from the without Morel periodicity also. So I am going to talk about first the parent Hamiltonian. So what do I mean by parent Hamiltonian? Parent Hamiltonian means I am going to turn off the Morel periodicity by setting capital G equal to 0. So that basically gives rise to two band model. So one is without flux, two band model. One is with flux, constant flux, two band model. So one if one write the Hamiltonian in momentum space, this is the effect, this is the Hamiltonian they will get, and one can say immediately because of there is real element in the Hamiltonian time reversal operator, just take the complex conjugate form and there will be time reversal symmetry, other symmetry will be absent. So this belongs to class A trivial. Similarly, this also even though time reversal is just by modulated by a reflection operator here, this also belongs to the class A trivial, that means not topology to begin with. So parent Hamiltonian does not have topology. Now let's go to the actual model by introducing small g. So there are two cases as I've said, no flux with flux. So no flux one can see from the ladder geometry itself. So if I write this corner atoms in one sublattice A, there is no real hopping there. So I can divide this ladder into two distinct sublattices. Hence there is a chiral symmetry there. So this basically takes in this form 1 minus 1 in the diagonal form, and because there is a real element, there is also a charge conjugation symmetry and time reversal symmetry of course there. So this belongs to the VDI symmetry which can introduce topology in the 1D model. Now let's go to the with flux case. In the with flux case, there is extra degree of freedom of constant flux through each placket. So one can see there by just modifying a reflection operator, one can find this the operator explicit form which belongs to the CI trivial phase. So in this case, Morel potential does not introduce topology. So as I have said earlier, my choice of interest band is lowest band, not the actual half filling of the largest. So how did this symmetry help me to find the topological invariant of the lowest band? So it turns out that this symmetry does not help actually finding the lowest invariant, because this Hamiltonian has full symmetry, and this and the lattice when one calculate the Berry phase or Jack phase for the lowest band, it turns out that they are not well contest. So how does it? So what is the help here? So it turns out that the Morel potential actually has the inherent inversion symmetry. Sorry, inherent inversion symmetry within the potential. So this is the potential form. One can see this is the interleg hopping value. Let's say for I am considering for j equal to 4. So this is gamma 1, gamma 2, gamma 3, 4. So gamma 2, gamma 2 for gamma 2, gamma 4 are same, and gamma 1 there is no corresponding value in the right side. So this has a non-centered inversion axis. However, if I choose to shift the index of small j to j minus 0.5, I can see a inversion axis with centered. So that means there is a centered inversion axis. So I am going to talk about this centered inversion axis for the next two cases. So similar with flux cases also, by changing j to j minus 0.5, I can find a centered inversion axis, but there is a additional reflection symmetry here. So it turns out that by this inversion operator, I can define an invariant, and by the Foucault invariant, I can define a topological invariant for any band. So it turns out that this is the actual topological invariant, unlike the Berry phase. So when I calculate this formula, it turns out that for no flux cases, for even values of j, odd values of j, for even values of z for greater than g, there is always topological. However, there is additional values of odd values of there is a band gap closing. That's why it is topological invariant, and there is a bulk boundary correspondence with the open boundary condition. However, in similar cases also found with flux cases. However, it turns out that these S sets are energetic. That means it keeps on changing when you change the parameter. So what is actually protected? So it turns out that actual protected is just one minute. The entanglement spectrum. It turns out that entanglement spectrum in addition 0 1 it gives 0.5 values also, and corresponding there is entanglement entropy, which is exactly mapping with the inversion invariant value. That means and this is same as with flow scales also. That means it turns out that Moray potential can introduce topology, Moray inversion symmetry, and this topology is insensitive to presence or absence of flux, as I have shown you. And main thing is bulk boundary correspondence doesn't manifest through physical edge modes, rather it manifests through entanglement edge modes. So with that thing, I'd like to conclude my talk, and thank you.
Thank you. Any question? Anyway, I have a small question.
Yes.
So at the end, you were talking about the entanglement entropy.
Yes.
So this potential has given you any special advantage in entanglement entropy? Because this type of there are several models. So here in this, using your Moray potential, is it your entanglement entropy is enhanced or any
No,
any
just
advantage?
so this is I'm calculating for finding topological value,
Yeah.
and this is just giving just like a singlet phase two lone two values.
But
So
actually, entangled entropy has then connection with quantum sensing.
okay.
So there, whether your approach has any advantage or not. So
So in quantum sensing, I don't know, that, but it's just theoretical. Yeah.
oh,